Yeah, thanks for the invitation. I mean, this is my first time, traveling somewhere else, and for actual giving talks or academic purposes. So I wrote a bunch of stuff down.
Subhash, it's up to you, but the rules here that the speaker is allowed to take off the mask. Whatever you want, you're allowed to do it.
Yeah, I think so.
I mean, just that probably you will hear me better.
Exactly. If it's okay with you. Yeah.
I wrote a bunch of stuff just to speed things up. So I will talk about approximability of CSPs, as in constraint satisfaction problems, on satisfiable instances. This joint work with Ame Bhangale and Dor Minzer. For those who sort of know what the topic is, here is just a 2-minute version, quick 2-minute version. So for CSPs, let's say 3-sat, there is a notion of basic alphabet. So 3-sat is over alphabet 0, 1. There is a predicate, which for 3-sat is the OR predicate X or Y or Z. And we know that it has a threshold 7/8, meaning given a satisfiable instance of 3-sat, you can find assignments which satisfy 7/8 fraction of the clauses efficiently, but it's NP hard to do better than 7/8. 7/8 plus epsilon is hard. So for linear equations, mod 2, so the predicate is X plus Y plus Z equals 0, and you can find a satisfying assignment, a fully satisfying assignment if there is one. You can take 3 linear equations, but over non-abelian group, right? Product of 3 group elements is the identity of the group element. We don't know whether there is approximation threshold, so I will say what the answer here is. This leads to the following 2 questions, which is kind of the focus of this talk. How about characterizing this precise approximation threshold for every CSP, not just for specific examples like this, and on satisfiable instances. So I stress the 2 words, every and on satisfiable instances. Okay? And this naturally leads to, as we observe in our paper, to a purely analytic question of estimating expectations of this kind, where ABC are inputs which have some joint distribution, and they are inputs from some hypercube. Okay, so that would be the analytic question. Now, for those who are not familiar with the basic terminology, here is a quick, introduction. So fix some alphabet sigma, which could be binary alphabet, and a predicate P is a map from sigma to the K to 0, 1. So think of K as constant, like 3 or 4. So the K will be called the arity of the predicate, and P inverse of 1. Formally, this will be the satisfying assignments to the predicate. So some assignments are called satisfying and some are non-satisfying. The rest are non-satisfying. So that's the predicate. And for every predicate P, you can define a CSP, constraint satisfaction problem. So this is a problem where you have n variables and n constraints. The variables are supposed to be assigned values from this alphabet. And each constraint, let's say C sub j, is the predicate P applied to some ordered subset of K variables. Okay, so structurally, this is going to look like a K uniform hypergraph. The variables are vertices, and these constraints are, k-ary edges. Given in such an instance, there are 2 questions you can ask. You can ask the satisfiability question, meaning I give an instance, determine if there is an assignment to the variables which satisfies all constraints simultaneously. So that's the satisfiability question. And the next question would be approximation question. If this is not feasible to do efficiently in polynomial time, given a fully satisfiable instance, find an assignment which satisfies some good fraction, some fraction alpha of P of the constraints. And I'm hinting here already that presumably there is a precise threshold, right, that you can do up to that and not beyond.
So the second question is independent of the first, in the sense that even if you cannot get, it's not just about the complexity. Even if you cannot get, maybe you can get some of it.
Right. It is about the complexity, but there are 2 different questions. When you want to get alpha of P efficiently, and maybe believe that doing epsilon better is maybe NP hard or some, infeasible.
But I mean, you want to solve it even if independent of the question whether a full solution exists or not.
Right. So this leads to separate questions. So for now, I'm assuming that the instance I give you does have a fully satisfying assignment. but algorithmically, you might not be able to find it. So algorithmically, you might only be able to find something which satisfies some 95% of the constraints.
There's different question. Before the different question, I just want to tell Alex, look at the example 3SAT listed there. 3SAT for satisfiable instances, we know that 7/8 you can easily do, really easily. You can find an assignment satisfying 7/8 fraction. And to do epsilon better, we know it is NPR.
So 7/8 is a sharp threshold?
There's a shape if you want to call it.
So in any case, everything I was going to explain, so it's only a matter of time. All right. So now here is it's like a small issue, but I will mention it. That sometimes for the CSPs, if you're not careful, it may just become trivial. So for example, for 3SAT, if this is your predicate, X or Y or Z, I could assign all the variables to true and satisfy all the constraints immediately, and there is nothing to it then. So to make it non-trivial, in the Boolean case, you allow negations, meaning the clauses are allowed to be of the type X bar or Y or Z. So you allow variables to appear in negated form. For linear equations, you may want to allow not just equations of the type X plus Y plus Z equals 0, which if you do, then you will just assign 0 to all the variables and you would be done. But I will allow only equations of the type X plus Y plus Z equals 1. So similarly here, X times Y times Z is some arbitrary element of the group. Okay. So this is what I meant by negations and allowing mix of predicates. So for example, linear equations where the right hand side can be anything. But we would agree that it's really the same template, right? So it's a mix of predicates on the same template. And sometimes this is not even necessary. So if you consider the problem of color the edges of the graph with 3 colors, vertices, so as to maximize the number of edges which are properly colored. So you have 3 colors. So, and the predicate is X naught equals Y. And here you don't even need any of these two to make it non-trivial. It's already non-trivial. So that's just
then what type of graph would you be considering?
No, the graphs are arbitrary.
The graph is the CSP.
The graph is the CSP instance. Right. Okay, so now let me quickly talk about some CSPs and their thresholds. So this is the threshold, this is the algorithm, and this is the hardness. So for 3SAT, we know that the threshold is 7/8. We know, meaning most of the results I will quote, they are considered huge breakthroughs in computer science. Okay, so when I say we know modulo these breakthroughs. So we know that 7/8. So now when I say that 7/8 is sharp threshold,
what that means exactly? What precisely you mean by 7/8?
Right.
Some of us are not really.
Yeah, exactly. Right. So you and I can ask questions, right?
Of course, feel free to ask questions. No problem. Now, when I say that 7/8 is a sharp threshold, clearly there is an algorithmic side and there is a hardness side, and they have to match exactly at that threshold 7/8. Meaning, I can design an algorithm which, on a satisfiable instances, finds an assignment 7/8 fraction of the clauses. Okay, which for 3SAT is actually easy to do. Just assign true or false.
So the theorem said that given any predicate like that, there exists an algorithm so that given anyone, he can find assignments.
Given a satisfiable instance.
What?
Given an instance for which there is an assignment which satisfies all the constraints.
We don't know.
Assume there is one.
Yes. Okay.
Then we can find an assignment which satisfies 7/8 of the
clauses for 3SAT.
In fast time.
In polynomial time.
No, but 7/8 what?
7/8 fraction of the constraints.
Of the constraints.
Yes.
So it's a family of equations, and you can satisfy 7/8. It's not that it's close to the true in 7/8 of the bits. That's not.
No.
I'm getting it now.
Okay, that's what I would like.
No, optimization problem. Maximize as many constraints as you can.
Okay.
Right. Now, for 3SAT, the algorithmic side is easy.
But you're always assuming that
Yes,
you can't. There exists a satisfiable.
Right. Now, for 3SAT, getting 7/8 is easy. you just assign random true false values to the variables. So you'll satisfy a clause with probability 7/8. So in expectation, you are going to satisfy 7/8 fraction of the clauses. So algorithmically, that's easy. You just take a random assignment. From the hardness side, to show that actually doing 7/8 plus epsilon itself is an NP-hard problem. This is a celebrated result of Hastad from mid-90s. Now for 3-lane over abelian group, well, of course, using Gaussian elimination, if you know that there is a satisfying assignment, you can find it using Gaussian elimination. And of course, then there is no hardness to speak about. For 3-lane over non-abelian groups, this I will actually describe what the algorithm is, and there is a sharp threshold, which I will write it down. So this is the denominator is the commutative subgroup of the group. Okay, so 1 divided by size of the commutator subgroup. So that's precisely the threshold. So I need to give an algorithm which achieves that guarantee, and I need to show also that achieving a guarantee beyond that is hard. So this we did in a paper with Amey Bhangale recently. So I will describe the algorithm just to give a sense that it's non-trivial, and there are many other CSPs where we know that the best algorithm is given by a linear programming or semi-definite programming relaxation. Don't worry if this is not clear to you what this means. It's some standard algorithmic method, and there are matching hardness results. So this is just to give you a hint that this is we are talking about non-trivial stuff, in the sense that the algorithms, they can be of very different kinds. You could just take a random assignment, you could do Gaussian elimination, you could do linear or semi-definite programming relaxations, this and that, okay? Or in the long run, one would have to have algorithms which combine all these three into some kind of hybrid algorithm, okay? It's actually...
Are there also results on KSAT? I think I've heard about
KSAT is exactly the same situation. The threshold is exactly 1 minus 1 over 2 to the k. Okay. Now let's look at this algorithm.
That's known to be sharp.
Yeah, that's known to be sharp, yes. Now let's do this algorithm for non-abelian group. Just to, G is non-abelian. So we'll define.
It can be abelian, it's a special case.
Yeah, it's a special case, right? So let this GG denote the commutator subgroup. So this is a subgroup generated by all elements RS, R inverse, S inverse, where RS are.
I don't understand something. If it's a abelian group, then GG is equal 1.
Yeah, and you get the one.
It's the order of GG. Not the index. So
that's right. Yeah.
So for abelian groups, you certainly get 1.
Yeah.
But for every other non-abelian group, you get something strictly smaller, and that's the precise number. But let me demonstrate that you can do this much algorithmically, because it's easy and it's somewhat, I guess, insightful. Yeah. So this is the commutator subgroup. Let H be the quotient of G by the commutator subgroup. And then what I can do is the following. If I have a system of equations, which is of the type x times y times z equals some constant b over the group G, okay, then I can move to the quotient group and consider the corresponding system of equations where x twiddle, y twiddle, z twiddle equals b twiddle over the quotient group, right? And since H is now abelian, this system I can find, because I'm assuming that there is a satisfying assignment. So this system has a fully satisfying assignment, and that one I can find just by Gaussian elimination. So I find the assignment to that. And then for every variable x, I assign a random value from its coset, because an assignment here, x twiddle, is really just a coset of the commutator subgroup. So just take random assignment from its coset. The coset x twiddle. Okay. And I will satisfy this equation. And therefore, this equation with probability 1 divided by size of that coset. right? And this is how you get this much approximation. So this is what one would do for a general non-abelian group. And in this paper, we also showed that doing even a little bit better than that is NP hard. Okay.
Can you just say?
And that's the hard part.
That's the hard part.
That's the hard part, which I don't want to get into. It uses techniques, combination of techniques which are by now standard, starting with the work of Hastad and even before actually, plus some new stuff with representations.
It's about estimating expectations.
Yeah, in the end, yeah, it's about estimating things of this kind. I will get to that towards the end.
In your setup, you don't care about whether you're getting a random algorithm or not. You don't care about the randomization at this point.
Yeah, so we don't care so much about de-randomization. And if you are in CS, you would believe that de-randomization, if we really care, we can always do it. So let's not even worry about it. So that's the viewpoint one would take. Okay, so
SDP capture that algorithm? Well, is there some SDP that captures that algorithm?
no, SDPs cannot capture Gaussian elimination. This is a fact.
Well, Prasad or Lorenzo has a way of doing something alternative to, replaces Gaussian elimination. You probably know it with various random sampling.
Yeah, right.
You know.
Yeah, but it's some, yeah. But it's not SDP.
It's not SDP,
Right.
but it's close.
Okay, so we can propose the following hypothesis that, that for every predicate P, there is some threshold alpha of P, some number strictly at most 1, such that on fully satisfiable instances, I keep insisting on the instance is known to be fully satisfiable. So on fully satisfiable instances, there is alpha P approximation, meaning you can find efficiently alpha P satisfying assignment on fully satisfiable instance.
Alpha P approximation is easy.
Yeah, meaning, there is an alpha P approximation. And that for every epsilon, alpha P plus epsilon approximation is hard. So we put the word hard in quotes. So ideally would like to say that this itself is a NP hard problem. Okay, though the current technology will not get us that far. So there are some lesser notions of hardness, which for now we might want to be happy with. Okay. So no, it's not completely clear that such a threshold has to exist, but it's consistent with our understanding and knowledge so far that such thresholds ought to exist.
Do you allow the trivial value 0 or not?
The 0 is sort of not meaningful because if you just take a random assignment, random assignment will always do 1 divided by the fraction of the satisfying assignments relative to, it should be the other way around. What is the fraction of satisfying assignment relative to total number of assignments to the predicate? So random will always do this. No, size of sigma to the k.
Okay.
So there is 0 is not particularly meaningful. Now, let's not worry so much about whether this threshold has to formally exist, but all indications are that it should exist. So this already leads to 2 questions, which are 2 topics I must talk about. And I think I should have said right in the beginning that, that the topic I'm talking about is very connected to many other topics. And even though I must talk about all of those other topics, I might end up not talking about some of the things I should talk about. So apologies for that. And also, so in the paper, we view our paper as starting this big project, which hopefully will go on for many years in the future, and maybe in 10 years or so might resolve this question fully. right? So, so this is just the beginning in some sense. Right. Yeah, but there are two directions I must definitely talk about. So first of all, now this question, at least for me, this is one of my favorite questions for maybe 10, 15 years, okay? But yeah, but we were completely stuck because even the very special case of this question is to first determine whether alpha p is equal to 1, okay? Meaning the satisfiability question, right? Given a satisfiable instance, can you determine if, right, or can you find the satisfying assignment to begin with, right? So for example, for 3 lin over an abelian group, this threshold is actually 1, right? So determining whether this threshold is 1 actually itself was a very very big open problem, and this was recently resolved. This is known as now dichotomy theorem, and this was okay. So I will state what the theorem is. The theorem states that for every predicate p, the corresponding CSP is either in polynomial time, meaning the satisfiability question is you can solve it in polynomial time, or it's NP hard. This sort of looks maybe what's the big deal? It looks self-evident, but it's not self-evident at all. This is, you know, I love this result. This is one of the results I'm truly fascinated with. Though I have to admit that I don't understand the proofs that well, because this is done via a machinery which is referred to as algebraic machinery. It's quite different than what I'm used to. I'm used to more analytic machinery. Yeah, so I have to admit that, you know, I love the result, but yeah, I can't say that I understand the proofs.
It took 30 years.
It took.
Conjecture that this is still exists for more than 30 years.
Right.
Achieved last year or 2 years ago. In
the last 2 or 3 years, and this was conjectured by Feder and Wardi, and this was resolved recently independently by Bulato and Zook. And in fact, it says something more. You can even, in somewhat indirect way, even detect which CSPs are in P and which ones are in P hard. So the classification is more meaningful than just saying abstractly is here or there. And that particular characterization, this was also, this was conjectured by Bulato, G-Wans, and Krokin. I'll state that characterization as well. But for now, right, we know at least the dichotomy theorem now. And now that we know the dichotomy theorem, yeah, now this should be the stepping stone towards actually resolving the question at the top. And almost certainly, if I intend to work on the question on the top, at some point I will have to understand the proof of the dichotomy theorem. I'm just postponing it as much as I can.
Sorry, one question here.
Yeah.
Do you expect the characterization on top to be the same as the characterization of distinguishing 1 versus at most alpha satisfiability?
I don't understand.
So I ask you the following distinguishing question. So for
oh, you mean distinguishing versus finding?
Yeah,
they are considered as the pretty much morally equivalent.
So this finding, given a satisfiable instance, is you consider the
same as distinguishing.
Yeah,
right.
Okay.
Yeah, so I would also have a question. So when you say polynomial time, I mean the different polynomials. Is there any quantitative?
Right. In fact, there was a comment I was going to make. So actually, what the theorem actually says is. No. You asked a different question. So what I was going to say is that those which are NP hard, actually the theorem says that they are NP hard because there is a gadget reduction from 3 sum. And once you have a gadget reduction, it also follows that there is some alpha which is strictly less than 1, such that doing beyond alpha is actually NP hard. And that's an argument in favor of these thresholds to exist in the first place. Okay, but you asked a different question that those which are in P, what can we say about the exponent of the polynomial? Yeah, I'm afraid I don't know the answer to that.
And another question: if you have a satisfiability,
yeah,
then do you know, are there terms that say how many are satisfiable? I mean, the existence of one may imply many others.
Oh, you mean count the number of satisfying assignments?
Yeah.
That's a completely different ball game. From the computational complexity perspective, those problems are extremely hard. Captured by a class called sharp P, which is way harder than NP.
Okay.
All right. So that's the dichotomy theorem. But that's in one direction, just determining whether alpha P is equal to 1. On the other hand, the other direction is instead of worrying about instances which are fully satisfiable, suppose I tell you that the instances are 1 minus epsilon satisfiable, meaning there is an assignment which satisfies almost all clauses or constraints, okay, but not quite all. Okay. Now, in this scenario, actually, it turns out this question is fully solved, and this is primarily work of Raghavendra. So there is a full characterization which I will. I'm not sure how I will do on time. If I get to it, I will even describe quickly what this Raghavendra's result is. Yeah, it basically gives a full characterization. It presents an algorithm which is based on a semi-definite programming relaxation and shows that that algorithm is the best possible one. It gives the right answer. Okay. So on almost satisfiable instances, this is done. But on satisfiable instances, it's a completely different ballgame. Now, so this result of Raghavendra, of course, we are very fortunate, right? So I could draw, smiley signs that we have a full characterization. But it's also a bit sad story that on fully satisfiable instances, it's a completely different ballgame. And I think much more complex and interesting game. Already Raghavendra's results is already fascinating. Okay, so we are just building on top of other. So I hope to at least quickly say a little bit about dichotomy theorem, a little bit about Raghavendra's result, and then what we do. And in particular, I think I will at least state the analytical question, which I think is quite really interesting, even independent of the applications. So the dichotomy conjecture, which dichotomy now theorem that every CSP is either in P or NP hard, right? So there is a CSP P for underlying predicate P. Now let me tell you when it is in P and when it is NP hard, and it's a very nice characterization. And the relevant notion here is what is referred to as polymorphism. Perhaps it will be more instructive to actually give an example of polymorphism before making a formal definition. So here is an example of what is called a polymorphism. So consider the predicate linear predicate x plus y plus 0 mod 2, right? So this is really the 3-lin over Z2. Now here is the following observation. So suppose I construct a 3 cross n matrix where these inputs are maybe I would call them capital X, capital Y, capital Z, because these inputs are multidimensional inputs. And let's say the number of dimensions is n. Let's say even 7, just for the sake of concreteness. Okay. And now here is what I will do. Every column, let's say the ith column, I plug in as xi, yi, zi, which is a satisfying assignment to the predicate. Meaning xi plus yi plus zi must be 0.
So each xi, yi, and zi is of length 3.
Yeah. So therefore, it's a 3 cross 7 matrix. Okay. Yeah, but each column is a satisfying assignment of the predicate. Okay. Now, once I do that, I will. Here is my favorite function, which is parity function. So parity of the bits xi I equals 1 to 7. So it's a function which is applied on the rows now. Okay. So if the row is capital X, capital Y, capital Z, I evaluate f of capital X, f of capital Y, f of capital Z. Okay, and I get out column. So I refer to as the output column. Okay, and now the claim is that if every input column is a satisfying assignment of the predicate, so is the output column. Okay, is it clear, right? Because if every column sums up to 0, in fact, the whole matrix sums up to 0, and therefore, if I take the row-wise sums, fx, fy, fz, they will also sum to 0. Right? So this plus this plus this is also 0, mod 2. And that's the property. This is what is polymorphism. If you construct a matrix whose every input column is a satisfying assignment to the predicate, there is this special function f referred to as the polymorphism, which if you apply to the rows, the output also becomes a satisfying assignment. So here is another example. This is example 1, this is example 2, and this is an example which is 2SAT. 2SAT, as you know, the underlying predicate is just x or y. Okay, and here you will have 2 rows, capital X, capital Y, and again, let's say 7 columns. Again, here nothing special about 7. It could be 9 or 11, any odd number. It has to be odd because I also want to allow equations of the type xi plus y plus zi equals 1. So it needs to be odd. So there is a small subtlety there. For 2SAT, there is any integer will work, 7, 8, 9, whatever you want. And again, you have the same property that if you plug in each column as a satisfying assignment to the predicate, and the satisfying assignment to the predicate are to 2SAT are 1, 0, 0, 1, or 1, 1. Okay. Then, if I apply a certain function to the rows, I will have to tell you what that function is, and construct the output column. That will also be satisfying assignment. Okay. And a function which works here is majority. So you could take f of x to be the majority of all the bits in the rows. Okay. And it's clear that if each column is a satisfying assignment, the 1 is already in the majority for each column. And therefore, if you take the majority of the rows, in the output also 1 will be in the majority, right? So again, we have the same property that if every input column is a satisfying assignment, so is the output column. And this is the characterization. Now, there are some predicates for which there exists such a magical function called polymorphism. Those are classified as in P. And those functions for which there is no polymorphism are in P hard. That's the characterization. Except for one caveat. One caveat is that there is always a trivial polymorphism, which simply it's called the dictator function, which looks at the input and just picks ith coordinate for some fixed r, in which case the output will be identical to the ith input column. And clearly that would be polymorphism. So you have to disallow that. Okay. Yeah, so that's it. So polymorphism, formally it's a function f from sigma to the n to sigma. And this n is thought of as another constant. This is not referring to the input size, which is more standard in computer science. Okay. Yeah, the definition is as follows, that if you construct a k cross n matrix, k is the arity of the predicate such that every column, let's call these, yeah, it's a bit, indexing is a bit of an issue. I call these capital X1 through capital Xn. But I hope you understand that every column is a satisfying assignment to the predicate. So call this maybe
X1i.
Okay, fine. X1i, X2i, xki. Okay, right. And if I apply f row-wise, f of x1 up to f of xk, then this output column is also a satisfying assignment. So this is what is a polymorphism. It may or may not exist depending on the predicate.
It is the sum of those, or this is the sum of the FIs, right? It's the sum of the FIs.
No, it's
No,
not.
it's just a chapter, and you ask whether it satisfies the predicate.
Each for each row.
You are given that for every column it
Yes.
satisfies the predicate.
Yes.
Now you apply S to every row,
Yes,
and you get another case input.
yes,
And
yes.
you ask whether this satisfies the predicate.
Yeah, yes, which means the sum.
Not the sum.
No,
Predicates can be sum.
It will depend on the predicate.
Oh, okay, all right.
Yeah.
No, in the examples you gave before. it was-
No, no, in examples, in fact, I gave one which was linear and one was the two-sat or.
That you had the plus, yeah, okay,
No, that was because of the predicate is plus. So here it will be or.
okay.
Right. Yeah, and yeah, the theorem, which is this proposed characterization by Bulato, Givons, and Krokin, and that's the eventual theorem that if there is non-trivial polymorphism, non-trivial meaning something which is not a dictator, then the predicate is in P and NP hard otherwise. If there is no such polymorphism, there are some subtle issues which you have to take care of. So I'm ignoring some subtleties, but on the whole, this is the characterization.
Any upper bound on n as a function of sigma and k?
Unfortunately, this is not the business I'm expert on, so I don't really know the answers to many questions on this topic. I think there should be some upper bound a priori, but definitely one issue is whether such a polymorphism exists for all values of n or only for some. Okay, because already, as I said here, this n will have to be odd. Okay, so there is this, that definitely is definitely a real thing. So
The theorem only requires for one n.
yeah, the theorem only requires for some n. Yeah.
But why does it have to be on the?
And if if it once it's for some n, you can do some sort of composition trick, and you can get for arbitrarily large n. So that's not the issue. That's not the issue. So there was a question.
I think I don't get it. I mean, for example, it can also be constant function.
So when I say non-trivial, you also have to disallow the constant function. Yeah. So non-trivial meaning no constant, no dictators.
But if there is a constant, it's very easy.
Mm-hmm.
Like if the constant is a polymorphism, then you can just use this constant to satisfy everything.
Yeah, that's some kind of trivial case. So let's not,
Are you
So
required?
another question regarding this conjecture or like solving this. I mean, I assume the hardness assumption is not unique games. You want bricks 2 to 1 or something.
Where?
So
In the dichotomy business.
yeah, in your stronger like dichotomy goal.
Yeah. So when I wrote that hard thing in quotes, so we are very far from even saying what hard there should mean.
Okay.
So we in paper with Dorr, Noam Lifshitz, and Mark Braverman, we propose something called rich 2-to-1 games conjecture. Okay. Yeah. So you will have to use that for sure. Plus, you will have to actually go into the proofs and get all the analytic properties right. And once you do everything that, hopefully.
And even then, the algorithm isn't clear yet.
Nothing is clear. As I said, for us, it's like the beginning of some potential 10-year project, which hope goes on for 10 years. Okay. On the other hand, it might just be dead end. Who knows? Right?
Just to be sure, there is no requirement about negative instances at all, right?
What do you mean by negative instances?
So nothing prevents me from doing a function that kind of overshoots by satisfying more things than it should, right?
It just has to work for any table.
Yes, but only on the positive side.
Yeah.
It means it doesn't have to be an if and only if.
No, it's not if and only if.
Or not even like.
If and only if it's kind of, you can see that it's too much to ask, but you could put, so it's kind of related to the fact of taking a constant function, right? Taking a constant function trivially satisfies this because you can map it to something that will certainly satisfy it, but you could kind of avoid the constant function if the predicate's not way too hard. You could kind of avoid the constant function kind of easily, right? Like for instance, take the or predicate. You could map the string 0 to 0 and any other string to 1, and you would probably be fine, I think.
Sorry, I got distracted by the clock, which was around.
Don't worry about the time. There are many questions and you get more time. So don't worry.
The question,
Let's do it.
negative requirement, right? This is really the.
Yeah, this is it. Yeah.
Okay.
I'm not hiding anything. Right. Yeah. So right. So now, of course, those which do have polymorphism, they are in P, and they are not of concern for us, right? Towards this finer characterization in terms of approximation. So we will worry about those which are NP hard, and those which are NP hard. It's standard to study what are known as dictatorship tests. Okay,
so just a second before you continue to approximation, etc. I just want to say something about this result. I mean, it should be clear that it's pretty amazing in the sense that it recovers all algorithms that exist, all polynomial time algorithms for all CSPs. Yeah, so and recovers others that maybe have not been known. Yeah, so Gaussian elimination.
Is it easy to see with this that you know 3SAT does not have such a function?
Yeah. Yeah, for 3SAT, I think it's easy to verify that they
right. Yeah. So so it turns out that
it's not obvious to me, but
no, it's not. It's not obvious.
Yeah.
But it's not difficult either. And this part is actually easy in the sense that if there is no polymorphism, then it's NP hard. That part is easy. So the difficult part of the dichotomy conjecture was to use the polymorphism to get a polynomial time algorithm. Okay, and then already, right, the polymorphisms, they could be qualitatively of many different natures. You could have linear and something which is non-linear, and presumably at the end of the day, you could have predicates where inside the predicate, there is some linear structure hidden and some non-linear structure hidden, and your algorithm will have to somehow figure out all those substructures and have hybrid algorithms, right, which are both linear as well as non-linear, and somehow combine the whole thing together. So yeah, as I said, this is real fascinating stuff. Right. Yeah, so now the predicates for which there is no such polymorphism, you can study what's referred to as the dictatorship test. So I will talk about the dictatorship test. And the dictatorship test, pictorially, it's pretty much here. Okay. So polymorphism means if every input column is a satisfying assignment, the output is a satisfying assignment. So now I can consider the following test where I will plug in a random satisfying assignment as every column, random from some fixed distribution that I can choose beforehand, and then look at the probability that the output is a satisfying assignment. Okay, and that's exactly what is referred to as the dictatorship test. So
you have to pick n.
Yeah, so for any function, it's a test on a function. So any function, yeah. So I will describe it. So this is referred to as the dictatorship test. So given a function f sigma to the n to sigma, you do the following. You construct this k cross n matrix exactly as before, right? Where every input column, you chose it to be a satisfying assignment of the predicate, but from some distribution mu, right? Mu on the set of satisfying assignments, which you chose beforehand, and look at the output, f of x1 up to f of xk, and then you look at the probability that, so the probability that the test passes is the probability that this output, f of x1 up to f of xk, is also a satisfying assignment. And we agreed that if it's a polymorphism, there will be some function which would pass with probability 1, right? Now, of course, we know that dictator passes with probability 1. So, in fact, in some sense, what we are trying to do is we are trying to check whether the function is a dictator. That's why it is referred to as a dictator test. Okay. So, from the property testing viewpoint, what we would like now is figure out whether given a function f, which is far from being dictator, what's the maximum probability with which it could still pass this test? Okay, so that's really the question that becomes the key. So this is the key question. If f is far from dictator, and I'm not going to define what this means because this is another, this would be another big distraction. If f is far from dictatorship, then what is the maximum probability that f may still pass?
So then, doesn't the polymorphism also always pass this test?
Yeah. Of course, polymorphism passes with probability 1, but we are now concentrating on NP-hard cases where there is no polymorphism.
Okay.
Also, where does mu come into play? Because it could be that mu is like a constant thing, and then
Well, you want a good dictatorship test, so you pick mu. So
You have to pick
yes,
mu.
who picks mu? This is the question, like in this definition.
As I said, yeah, I agree. There are many questions. Okay, so hopefully, at the end of the day, it's a tussle between do you think yourself as the algorithms player or the hardness player, right? And depending on whether you're from this side or that side, your objectives are different, clearly. And the whole point is to figure out the sharp threshold in the middle, such that both sides match. Okay, so if I'm the hardness perspective, then I will have to pick mu cleverly so that this maximum probability is minimized. Okay? Yeah, this is my goal as a hardness person. And whatever this maximum probability that such a function still may pass, let's call that probability alpha of p. Okay, and now I'm hinting already that that ought to be the threshold, the right approximation threshold. Okay, so at least morally this is the case. Okay. Now, of course, I will pick alpha. I will pick mu cleverly so as to minimize this, right? As a hardness player.
Is the minimum over mu with maximum over.
Right. At least as a first level of consideration, everything gets much more subtle. So that's really, and I hope you can already see that this is in some sense this is a purely analytic question, right?
when you said this is morally the case, this is also what examples like 3-sub, the way 3-sub was proven to be 7-8 hard is exactly like that's like.
So that's the dictatorship test. So the dictatorship tests, they have been studied in the area of hardness of approximation, which is also referred to as the PCPs or probabilistic checkable proofs, since early mid-90s, actually, starting with the work of Hastad. And in some sense, it's only in hindsight now that we know that this polymorphism and the dictatorship test, they were one and the same thing. Okay, but this was the PCP community, and that was the people working in the dichotomy conjecture, which roughly is referred to as the algebraic community. And I most certainly did not know anything about that topic until about, I guess, about 10 years ago, when Gabor Kun and Mario Sagedi, they had this really nice paper where they showed this connection. Or at least that's the paper where I learned it from. And the goal of that paper, the Kun-Sagedi paper, was the dichotomy conjecture. It was still open back then. So they proposed that let's attack the dichotomy conjecture using purely analytic methods. So formulate it as a dictatorship test and worry about probability of acceptance. And actually, I would have been super happy if they had, if that approach had succeeded first. Yeah, but somehow it didn't work out that way, and the algebraics they eventually did it anyways. And one of my hopes in this project is that eventually this might lead to analytic proof of the dichotomy conjecture, which at least I would probably understand it better. But I also sort of see that there is no way of doing it analytically without actually understanding the algebraic proof. So probably one has to understand the whole algebraic proof and then simulate each part piece by piece analytically, and of course, somehow put the whole thing together. God knows how. Right. But if there is one paper I would recommend, that would be this Kunsagedi paper. So this is very nice. All right, so that's all about dictatorship test. And then there was the second direction, which is the work of Raghavendra. So he considers instances which are only near satisfiable. Okay, so almost satisfiable. But in this case, he completely resolved the question that there is a threshold, let's call it beta p, which might be different from the threshold on satisfiable instances, which we denoted alpha p. So he says that there is some beta p for every CSP. There is some beta p such that you get a beta p approximation, and this approximation using STPs. I wrote down STP there, which I will show you in a minute. Beta p plus epsilon approximation is, well, ideally you would like to say NP hard, but this is assuming the unique games conjecture, which if you know, fine. If you don't know, you can forget it. So that's Raghavendra's result. Actually, there is even subtler point here that this is not strictly true. There are some CSPs which are what are called robustly satisfiable, meaning on 1 minus epsilon satisfiable instance, actually algorithmically you can find 1 minus epsilon prime satisfying assignment where epsilon prime tends to 0 as epsilon tends to 0. Okay. So in particular, this is what happens for max cut. On 1 minus epsilon satisfiable instances, you can find 1 minus square root epsilon satisfying assignment. Okay. So those are called robustly satisfiable CSPs. But there is a full characterization of robustly satisfiable ones, which was conjectured by Guruswamy and Zhao and proved by Bartho and Kozik. So there is this another class called robustly satisfiable. If you leave that out, right, then there is a threshold, right? Beta p, such that this holds. And this, of course, is meant to hold for every epsilon. And yeah, so let me say what Raghavendra, yeah.
Beta here does not depend on epsilon, except for that robustly.
Yeah, except for that separate class, this beta p is some fixed thing. Okay. And for every epsilon, this holds. Okay. Now, this is what Raghavendra does in hindsight. You define a family of algorithms which are based on what is known as semi-definite programming relaxation. So I wrote down one relaxation here. I mean, just so that you know that this is something completely concrete. I mean, there is no mystery here. Okay. So there is a predicate P. You have variables, constraints, which are collectively referred to as the instance. And then you write down what is called a semi-definite program. It's kind of a semi-definite program is a more advanced version of a linear program. There are with the variables and constraints, you have vectors attached. You have all sorts of constraints between vectors. It doesn't matter what this is. Okay, whatever it is, you can write this program and solve this program, and you get a solution to this program, which you use to actually find an assignment to the instance. Okay. Now, formally, you can define a quantity called integrality gap of this program, and this is what this parameter beta p is. Beta p is integrality gap of this SDP. So formally, it's the following. It's the minimum value of the optimum. So on any instance I, there is a notion of optimum. How much the best assignment could possibly do, right? The maximum fraction satisfied by any assignment whatsoever. On the other hand, when you write down the SDP relaxation, it's a relaxation, so it outputs a solution which could do even better than the optimum. Okay, and you will only look at those instances for which what the SDP gives you is at least 1 minus epsilon. Okay? So this is how you define this quantity called integrality gap. It's some formal quantity which exists. Okay, you'll have to, instead of minimum, take infimum. You have to take limit as epsilon tends to 0. I'm leaving all of that. Okay? You do properly, there is a quantity called beta of P, which is some abstractly defined, indirectly defined quantity, but is there. Okay. And then he proves that that's the precise approximation threshold. Okay. And this kind of emphasizes a point which I didn't say so far. Okay. That when we say that come up with this precise threshold alpha of P or beta of P in this case, it could be indirectly defined. In fact, your algorithm and hardness sites, both of them could even be defined in some abstract indirect manner. Right? I'm fine with everything. All right. So how much time should I take? Well,
10 minutes. We want to see the analytics.
Yeah, so I will show you the analytical part. So how about I will just say 2 words about what Raghavendra does, then right, and how it leads to the analytical question. If I had to say something in like a minute, and then I will tell you the analytical. Right. No, because even the stating the analytical question will take some time. Okay. So yeah, so what Raghavendra does is there is this abstract quantity called beta P, and then you get an algorithm which is beta P algorithm. This actually comes for free. This is just by definition, because by definition, on any instance which is 1 minus epsilon satisfiable, you compute the SDP relaxation, it will automatically give SDP value which is also at least 1 minus epsilon, and therefore the optimum have to be at least beta P, right? So you already distinguish between the cases which are 1 minus epsilon satisfiable and at most beta P satisfiable. Okay, so it's automatic. So algorithm comes for free, like it's by definition of beta P. On the other hand, for all epsilon, by definition, there is an instance I that is beta P plus epsilon integrality gap instance. Meaning it's a concrete instance of the CSP. It has variables, it has constraints, it has the SDP solution which is defined by vectors, such that the SDP solution amounts to having value at least 1 minus epsilon, but the instance itself is at most beta P plus epsilon satisfiable. Right? So it's a concrete instance. However large it might be, it might have 5,000 variables for all you know, but it's a concrete finite instance. Okay, and then from out of that instance, he concocts a dictatorship test. So if you recall, in the dictatorship test, there are these distributions mu. Okay, they come from that instance somehow. Yeah, so he uses this concrete integrality gap instance to build a dictatorship test. And once you build a dictatorship test, there is a standard PCP machinery which allows you to then prove NP hardness results modulo the unigame's conjecture. Okay, so that's roughly roughly what he does. That this integrality gap instance implies a dictatorship test, which then implies the unigame's based hardness. Okay, so now, yeah, if I had 15-20 minutes more, we could do something. I could say something a bit more enlightening. But since we don't, let me just say the following: that in Raghavendra's this scheme to work, your dictatorship function, the functions which you are trying to test, they're of this kind, right? Sigma to the n to sigma. Somehow this analytical machinery can only handle things where these functions are low degree. Okay, right? For some definition of low. So somehow you need to, if the function f had high degree part to begin with, you somehow need to get rid of it. Okay, and that Raghavendra manages to do just by introducing noise. Okay, so because we roughly know, right? Noise kills high degree part. That's some sort of meta statement. So introduce noise to kill the high degree part of F. When it get to the raw details, what it means is that the distribution mu, which you were using in the dictatorship test, ideally we would like it to be completely supported on precisely the satisfying assignments. But then Raghavendra says, okay, let's do that with only probability epsilon. But with probability epsilon, let me just pick any uniformly random assignment from sigma to the k. Some of them are going to be non-satisfying. Okay, and this is what leads to the so-called imperfect completeness. Because now, because of this noise, even dictators will not pass with probability precisely 1. The dictators will only pass with probability 1 minus epsilon. And that's what it leads to imperfect completeness. And therefore, the result holds only on almost satisfiable instances, okay, as opposed to fully satisfiable instances. And this distinction between satisfiable versus almost satisfiable, it's not, how do you say this? It's not minor, it's something fundamental. So, for example, if you have a system of linear equations mod 2, then of course we know that on satisfiable instances, we can find the satisfying assignment. But on the other hand, on near satisfiable instances, actually it's hard to beat the random. So you have a hardness result of 1 minus epsilon versus half plus epsilon for 3 ln over Z2. This is another celebrated result of Asta.
Which uses this idea.
Which uses this idea, exactly, right? So this is all, these are fundamental things. These are not, just hacks which you can somehow get around by. And this whole issue of linearity also is the crux of the difficult part of the dichotomy, proving the dichotomy conjecture itself, right? How are we going to deal with linearity? And this linearity, it manifests itself in all kinds of different ways. They, of course, are all related to each other, and somehow everything has to fit together. Okay. And now, since we are insisting on characterizations on fully satisfiable instances, the main issue, at least at a technical level, is that we cannot have noise. Our distributions have to fully be supported only purely on satisfying assignments. Okay. And still, we would like to somehow say that I don't really have to care about the high degree part of the functions. It gets killed anyways. Okay. So that leads to the analytical question that what are the predicates such that if you have, let's say, a distribution with full support on P inverse 1, the high degree part automatically gets killed. Okay. And this question itself will be the analytical question, which turned out to be surprisingly hard. I mean, either it is hard or we are not good enough. Okay. So I will state the analytical question. And we are able to solve this analytical question, make some progress, and then also prove some partial results on hardness of CSPs, this and that. So I will not describe any of that, and straight away state the analytical question. So here is the question. In fact, let me probably explain it by an example. So let's take our predicate 3 ln Z2. Right, we'll come back to this. This example we already saw before. Suppose I pick 3 inputs, X, Y, Z, such that each column is a satisfying assignment. Now, this is the predicate 3 ln. So each column is Xi plus Y plus Zi equals 0 mod 2. Okay. Now I claim that there exists a function, and this dimension is supposed to be n. I claim that there is a function f, right? It's a function of the row, right? In this case, it's just a parity function. So f of, let's say, x is simply, I will sum up the parity bits, I equals 1 through an xi, but I have to take the parity, so minus 1 to that. Okay. It has the following property, that now let's even say I picked an assignment such that xi plus yi plus zi equals 0 with respect to some distribution mu on the satisfying assignment of the predicate. Right? Then what's this value? Expected value of fx is the same function, fx, fy, fz. +1, right? Because if each column has 0 parity, the entire matrix has 0 parity. Therefore, if you take the parity of the rows, fx, fy, fz, their parity themselves is also 0 total. And therefore, in the +-1 notation, your expectation will be +1, right? And this expectation, to be precise, is over the 3 rows, x, y, z, which are picked in the following manner, that on each column, you have some underlying distribution mu on the predicate, and each column is picked according to that, okay? And let me emphasize that this function f is a high degree function. It's a purely high degree. It has no low degree part whatsoever. Okay, or
the monomial reflects that.
It's in fact a monomial, right? And this is the analytical question. For which predicates can there even exist a high degree function such that this expectation is non-negligible? That's the analytical question.
Would you say that again?
Yeah, so, okay, so that was like 10-second version. Now comes the 5-minute version. All right. Now you would agree that the same trick will also work over not Z2 but any abelian group, right? So what I could do is, so that's example 1. So here is example 2. I could again, let's say it's a 3-lin, though that doesn't really matter as such. It's XYZ such that XI, YI, ZI. These are 0, but in some abelian group. In abelian group, right? I could do the same thing. I could take my function f of x to be, I will sum up the elements I equals 1 through n xi in the group, right? And then apply some standard one-dimensional character of the abelian group. And I will get the same thing, that expected value of fx, in this case, fx, fy, fz, will be 1. Okay? And I could extend this bit more, that let's say I have any predicate P. It's a 3-ary, but the same thing holds for any k-ary predicate. Suppose the predicate itself is some abstract predicate, but suppose I was able to embed it into an abelian group, meaning suppose there was some map from the symbols to an abelian group G. Okay, such that all satisfying assignments under this map, they just became group equations. Okay, right? That for all A, B, C, which are the satisfying assignments, sigma A plus sigma B plus sigma C is 0. So suppose this was the case, right? Then the same thing will work. If you picked every column according to the predicate, there is some function that you can apply to the rows, which is a high degree function, which is exactly this. It's just that the symbols we are mentally identifying with abelian group elements. Okay, and you will get a high degree function f such that this expectation is 1. Okay, and our hypothesis, I could call it a conjecture, but you know, about 20 years ago, I made a couple of conjectures. Both of them turned out to be right, or hopefully right. And since then, I'm afraid to call anything that I say as a conjecture. So I just call it a hypothesis. Okay? So here is our hypothesis.
It will not protect you.
It might not protect me. Okay, fine, from some lawsuits, but I can take as much care as I can. So our hypothesis is that this is the only way. Via abelian group embeddings.
So that's the only way means that,
Meaning
that if there exists such an embedding, then clearly it works.
Right.
By definition of what you just said.
Right.
And if there is no such embedding,
then if the function f is high degree, then this tends to 0 as degree tends to infinity.
can you write it down? So this hypothesis, I will write it as cleanly as possible, so that if you actually pick up the statement and work on it, you could.
And let me state it for 3-ary predicates, but the same thing for k-ary predicates. So hypothesis, let's see one make our predicate, the alphabets for three locations or 3 coordinates to be potentially different, just to make it more general or cleaner. So this is the predicate. Now suppose there does not exist this group embedding, meaning there do not exist maps sigma, little sigma, little phi, little gamma, which embed these alphabets into some abelian group. Okay. Such that G is abelian. Moreover, that at least one of these is a non-constant. And you have to have some non-triviality. And okay, so that's the condition. There is no such embedding. Okay. Then for any essentially high degree functions, let's say the degree parameter is here.
Is in this monomial representation.
Yeah, so
you're assuming the characters of the group, and you are just
right. No. So you have to be a little more precise, because that there is a distribution mu on the set of satisfying assignments. So you have to express everything according to that distribution. Meaning, if your distribution on your alphabet symbol is non-uniform, you'll have to set up all your Fourier basis with respect to that non-uniform distribution.
Yeah, you take the Fourier,
right?
Yeah.
But then up to that, you're right. The degree means the monomials are of high degree. Except that what happens is that we also want our functions to be from sigma to the n to bounded range, -1 to 1. And it's difficult to achieve bounded. It's even difficult to come up with actual example, which is of purely high degree and bounded. Okay. So morally speaking, you should really think of it as, when I say essentially high degree, what I really mean is start with any function and then take out the low degree part. And the low degree part is defined as the Beckner operator 1 minus t sub 1 minus 1 over d applied to the function. So this is the low degree part, and then you take away. So this is what I mean really by essentially high degree function. And this keeps the boundedness.
Sorry, that's
What's the T or semi-group?
This is an yeah, I think it's a semi group.
The Boolean version, yeah.
Right. Right. And it's an averaging operator. So if f is bounded, this is bounded, and therefore f minus that is also bounded. So this, okay. And it has the property that the Fourier mass of all monomials beyond degree d becomes negligible. So it is essentially high degree. So this is what I really mean by saying essentially high degree. So for any essentially high degree functions, let's say f1, f2, f3, and these will be functions on sigma to the n and bounded. This will be from to the n -1, 1, gamma to the n to -1, 1. It holds that expected value over yeah, if you pick 3 inputs, right? X, Y, Z in mu to the tensor n, exactly like this, right? It's 3 cross n matrix where every column is according to mu, and mu is fully supported on the set of satisfying assignments. Then you look at f1 of x, f2 of y, f3 of z. This thing is at most little o1 d, meaning it tends to 0 as d tends to infinity. Yeah, so that's precise hypothesis.
So being a non-constant becomes not even almost constant, given what you said there.
No. Here things are discrete. So
I see.
If it's non-constant, it's non-constant. There is no notion of approximation there.
Yeah.
So that's the hypothesis. Of course, you can propose the k-ary version of this exactly same way. Now, what we can do is, so this is the paper. Now, of course, in addition to coming up with some actual applications, setting up the whole framework and direction, this and that, in terms of actual analytical result, what we can prove is we can prove this in the case where the predicate is 3-ary, and moreover, so the predicate, it's a 3-ary predicate with, let's say, alphabet sigma, phi, and gamma. And suppose in addition, you have the restriction that for every A and every B in sigma and phi, there exists some C in gamma such that ABC is a satisfying assignment. And moreover, for every A and every C, there is a B, which is a satisfying assignment. So in some special case, we can do it. Maybe we were just not good enough, but even this turned out to be quite a bit of an effort. And
but what if these assumptions allow you you relate this to being embeddable in a group, in a Billion group? What about these assumptions?
I wish I had a short answer.
You don't have a short answer.
I don't. Generally, we don't understand this business very well. But this we can do, and the way we can do this is we can somehow start with this predicate and have a sequence of transformations, keep changing the predicate somehow, and eventually reduce the whole analysis to the one case that we sort of understand, which is equations over non-abelian group. Okay, so here is a predicate which is take a group G which is purely non-abelian in the sense that it does not have dimension 1 representation. Okay, so I think it's called quasi-random group. I'm not sure. So it has no dimension 1 representation.
Random wants it to have high minimum. Except for the trivial representation.
Right, and then you can consider a predicate which is linear equations over that. So you will have all x, y, z such that x times y times z is 1 in that group. So if you take that predicate, then you can use some standard representation theory based analysis, which kind of mimics our standard analysis of 3-lin over abelian groups, if you know what I'm talking about. You just mimic that and you get what one needs. So this case, which is equations over non-abelian group, this one can do with standard representations theory, and this case of 3-ary predicates, this special case, we can somehow reduce it to it by sequence of.
You need to reduce it to a family of groups like this in order to drive the.
No, we just get one group.
One group, and I see. So depending on the degree alone.
Yeah, depending on the predicate that you start with. No, the degree is a separate parameter. I'm saying when I say I reduce, I mean we keep changing the predicate. So you start with some predicate, and you keep changing the predicate, and eventually come up with some group. Of course, that group will have to be derived from somehow the predicate itself. But then you eventually are able to apply the group analysis, and that works. Now, this really wasn't, the group case itself is not new. This new, and in fact, this is what we used in this paper with Amey Bhangale. But for example, one case which is new from our results is I hope it's new, and even if it's not that I care so much, is you could take arithmetic progressions over the same purely non-abelian groups. The satisfying assignments will be A, AB, AB square. So this case will be included in our case, among the predicates that we cover. Right. Yeah, if I had 5 minutes, I could show you the quick, nice proof of how it works with representation theory in this case, in the non-abelian group equations case. Right. Yeah, so that's about it. So I think, so this we wrote it up when we submitted. I think we can do the full 3-ary case without these restrictions. And I hope we at least have a good roadmap of how to do it for arbitrary k-ary predicates. Yeah. And then there is this whole big issue of how to use this to solve our characterization of CSPs, which amounts to even proposing a hybrid algorithm, which does all kinds of things, solves SDP, solves abelian group equations, maybe do something else, combines everything, comes up with some approximation algorithm, and then show that everything that this approximation algorithm does, you can mimic from the hardness side, right? And again, there is this tussle, and hopefully they should meet right in the middle. Right. That would be, you know, if and when.
All right. So questions, you can also ask a question about how this analytic proof works, what you can ask other questions.
So if there does, like in the cases that there does exist a Boolean group embedding, then like the parity thing is not only high degree, it's also like in terms of entropy of the Fourier thing, it has very low entropy. So maybe a natural conjecture if something is high degree and also high entropy.
Yeah, you could
let him finish because you know what he's talking about.
Right. Yeah. Okay.
Yeah. So you know, so also high entropy. Maybe this will imply that.
You're absolutely right. So you could prove all these things, and then you could further stare at the proof and get more things out of it. Right. For example, if you achieve this high expectation, then not only that there has to be this embedding, but these functions which achieve high expectation, they must necessarily use that embedding, which stands to reason. Right? And presumably the only way to use is to construct these few monomials. And that's it. So probably these functions should have a representation as constant number of monomials which are constructed from the embedding.
And are you essentially only using the fact that they all rely on different sets of variables such that the dependency graph between them is sparse? You don't care, I guess, like here you have, you know, x1, y1, and z1 are dependent on each other, and the same for x2, y2, z2. But probably you just need the dependency graph to be sparse. Like
it's not so much about sparse versus non-sparse. I mean, you could have something which is fairly dense, but still linearly embeddable in an abelian group.
Sure. But on the other hand, like maybe as long as it's sparse.
So I can tell you one very general result which is known, which was already known. This is the result of Alcaran Mossel. So he already handles his results, already handle the case when the predicate is connected, so to speak, meaning, so what is a predicate? It's a set of satisfying assignments. Okay. If you could, within that set of satisfying assignments, if you could move from any assignment to any other assignment by changing one coordinate at a time, okay, then it will formally be connected as a subset of that hypercube. Yeah, in that case, this is true. All these claims are true.
Yeah, we had talked about.
But as you can see, this one that we can handle now, it is not connected.
More questions?
Yeah, so maybe as an intermediate goal towards the algorithm, do you think it's possible that dynamic SOS will work? It's not known.
What is that? Dynamic?
So there's a dynamic version of the SOS hierarchy.
Dynamic, yeah, I don't really know what dynamic version is.
So it's the same proof system definition, except now in the intermediate steps, the degree is allowed to be much higher than your allowed degree.
Okay.
Okay, and
so I suspect that in this algorithm, the SDP component of it,
yeah,
probably I don't think it should be any different from which Raghavendra already uses.
Yeah, exactly. So dynamic SOS, it not only supersedes the SDP, but it's also known to capture Gaussian elimination.
Okay, right.
I mean, but that's the only thing. I mean, I don't know if people have shown that it captures the dichotomy algorithm.
Yeah, I don't really know. Yeah.
But yeah, it's just one suggestion that comes to mind that captures both of them.
Right.
That, but it's not known to be automatizable. That is, like, it's not known that you can find the proof quickly. SOS, this is known. Dynamic SOS is not known.
Oh, okay. All right. Okay. I guess I can take a look. Yeah, I will take a look. Yeah.
I guess a natural attempt to extend it to k-ary predicates is to look at longer arithmetic progressions.
Sure, sure.
That's a special case, and we know at least, I mean, this is totally syntactic. In the arithmetic combinatorics world, jumping between three-term arithmetic progressions, a higher term, was a big leap, and we understand today that you don't use Fourier analysis, you use, Gauss norms and so on. Do you see any relevant at all to?
So it's a good point. So this is one of those projects where we had innumerable false starts. Okay, we thought we could do it, but there was always some hole. So I remember there was this one stage where we thought we could do the full k-ary case, and we thought that implies the case for four-term arithmetic progressions. However, the considerations are a bit different. We did look at the math literature, and there they consider four-term or more higher arithmetic progressions for any non-abelian group G. And for them, the group G itself is increasing in size. For us, we come from the CSP motivation. So for us, the group is really fixed. Okay, and what we are really concerned are functions on G to the n. Okay, so put it differently, our methods could in principle do the case for four-term arithmetic progression, maybe even all arithmetic progression, provided it's some fixed group G, but powers of that, G to the n.
They do look at this. I mean, they look at arithmetic progressions in hypercubes. They do.
Yeah. So if
there you need higher order for your analysis.
So I don't see that. So far, I don't see that we need any of that. But we are doing. Yeah, but we are doing maybe some special cases. We also have somehow this consideration about only worrying about functions of high degree. So there could be some mismatch between the emphasis and the But we definitely did look at the literature on four-term arithmetic progressions.
More questions?
Yeah, so Schaeffer's theorem is a lot easier than the dichotomy theorem. So can you do your things in the Boolean case?
That's a very good question. So the question is the following, that the dichotomy conjecture, if you only were concerned about CSPs over Boolean alphabet, then this was already done like decades ago by Schaeffer. Okay, so the question is, so if your alphabet is Boolean, does that, the corresponding question about approximability, for us, does it make it easier? Yeah, and the answer unfortunately seems no. We encounter, this analytical problem would again arise, right? So unless we settle this analytical question, I don't think we can move forward, really.
Okay, thanks a lot.